So I'm going to talk a little bit about LLM inference and the various levels of the stack that we're building here at Red Hat and are working on in the community. And I think just an overall theme of this talk is going to be about how the transformer architecture is really at the core of all of the subsystems that we're looking at up and down the stack, from the inference engine all the way up through the cluster level. And most of what we're trying to do with making these subsystems is to exploit the intricacies of the transformer architecture to make things run faster. So we'll talk a little bit about a systems view to how we do all these things, and hopefully put some context around what's happening inside of this kind of fundamental infrastructure. So first, to just start, as Sally mentioned, I've been working on VLLM for the last couple of years, and really VLLM's goal is to build the fastest and easiest to use open source LLM inference and serving engine. So VLLM is that piece of software which sits at the core of most subsystems of systems that are deploying LLMs. So VLLM's job is to take a model like Llama or Mistral or DeepSeek, whatever the kind of model is, and make that go as fast as possible on the hardware that it runs on. And this is a really important problem because LLMs are large. They require a lot of compute, billions, even some models now with trillions of parameters, and the hardware that they run on is really, really expensive. Hardware accelerators basically are needed to do all this. And so VLLM's job and core mission is to make that as efficient as possible, to make the amount of hardware resources needed to serve models as small as possible. And really importantly, we try to make that as easy to use as possible, which a lot of other systems in this space have. And so why does something like VLLM need to exist? Why is there a need for specialized hardware, or specialized software to serve an LLM? And it really comes down to production serving of an LLM system is a hard problem. So importantly, we deal with batch size greater than 1, which means that there's multiple concurrent users in the system. And so VLLM's real job is to manage all of these requests at the same time. And I'll talk through in a second why that's a really hard problem. But another key piece is we're working with data center class GPU hardware. So these are massive machines, they're really expensive, and so VLLM's job is to really efficiently schedule all of these requests, manage the internal state of all of those requests, and make those GPUs go as fast as possible. And why is that greater than batch size 1 with multiple requests a challenge? Why is there a need for specialized software? So I'm just going to talk a little bit about how LLMs work under the hood to give a sense of this. So a model like Llama, for instance, is basically a function which computes the probability distribution of the next token given a sequence of tokens. So this equation I have here is basically the probability of x sub n given x0 ... x n minus 1. And that's effectively what Llama or any sort of LLM is a function which basically, given a sequence of tokens, predicts the most likely next token. And so when we turn to inference, it's actually not one single forward pass through the model that's used to generate the text. If you've ever interacted with an LLM system, you might notice that it generates one word at a time in sequence. And what's happening under the hood is what I show on the left-hand side of this chart, where if we get a prompt that's 3 tokens, like the quick brown, we run one pass through the model to generate that 4th token, the quick brown fox. Then given that sequence of 4 tokens, we pass that off to the model again to generate the 5th token, the quick brown fox jumped, and so on and so forth. So this is what's called an auto-regressive model, where we continuously chain calls to the model over and over again to generate 1 token at a time. And this makes LLM inference really, really, really hard and really, really compute intensive, because one request, to generate 1,000 tokens, which is a pretty standard request, will require 1,000 passes through that trillion parameter model, right? And this is a really, really big problem for a couple of reasons. One is there's a lot of latency associated with that, right? If you think about your average request to a chatbot, it can take 30 seconds, a minute, even more for some of the thinking models that are out there today. And so we really need to be able to interleave requests together and make progress on multiple requests at the same time. So very static, naive batching techniques are not going to scale well and are going to incur unacceptable latency. And then secondarily, this multiple passes through the model effectively implies that there's an internal state that needs to be managed during the LLM process, during the LLM generation process. And this contrasts with more traditional models that you might have seen, like BERT, YOLO, traditional predictive models where there's no actually internal state, and the way that the servers work is they get the request, pass it through the model, and then return the response. And so the key challenge that we're fundamentally solving inside of the LLM is this. We have the fact that we need to have multiple requests in the system at the same time, and that each one of these requests is going to be generating a sequence. And so the first kind of key problem and key innovation that BLM had, and inference engines have, is a shift from what's called dynamic batching, which was used by more traditional servers, into continuous batching. Dynamic batching is a strategy that's used for more traditional predictive models. As I talked about, predictive models don't have this autoregressive nature in them. They take an input, like an image, they run that image through a model, and then give you back a prediction. So there's no kind of state to manage. There's no multiple steps in that overall inference process. So traditional servers, and really prior to VLLM, we saw traditional servers employing what's called a dynamic batching strategy, which batches requests together at the request level. So for instance, like in this case, I have just a dummy example here. We have 4 requests. And what happens is those 4 requests, the first one has 3 input tokens, second one has 2 input tokens, third one has 3, fourth one has 4. And so what would happen if we batch at the request level is that we would wait for 4 requests to come into the server and then dispatch all of those off to the model at the same time. And all of those requests are going to execute in unison. And so you can see here in this example, the first request maybe generates 2 tokens, the second request generates 5 tokens, the third request generates 2 tokens, and so on and so forth. But what we can see is that since the third request only generated 1 token, we're going to have that wasted compute. There's space in the batch where because we're batching at that request level, we have to wait until that second request, which generated a lot of tokens, is done. And so you can see that this less granular batching strategy really, really hurts our performance because we have this huge amount of wasted compute because the batching is not happening at the iteration level, it's happening at the request level. And so the first key innovation that LLM servers had was to shift from this coarse-grained request level batching into a more finer grained, what we call continuous batching. And with continuous batching, we can exploit that autoregressive structure of the transformer to batch at a more granular, what I call the iteration or step level. So in this alternate example, when request 1 generates its first token at t step 4, generates its second token at t step 5, and then generates a stop token at t step 6, we're able to then remove that from the batch, add a new request in, and continue generating. And so you can see that with this kind of iteration level batching, we're able to effectively maximize the number of requests that are running on the GPU. And this is a small example, of course, where we only have 4 requests, we're only generating 5 tokens, but you can imagine that at the scale of requests that we have now with thousands of tokens inside of any individual request, this strategy is absolutely critical to having good latency for requests. So this is kind of the first fundamental change that we had in BLLM, was to shift from a dynamic batching to a continuous batching strategy. Okay, then the second piece that we have is, I talked before about how an LLM is a function which computes the probability distribution of the next token given a series of tokens. So another really obvious optimization is to think about how can we avoid recomputing all of those tokens from that same prompt over and over and over again. So effectively, what we try to do is to shift from a function which does, the probability distribution of x sub I given, x less than I minus 1, to a function where we can reuse some of the internal states of the model. And this is what we call the KV cache. So it turns out that there is such a thing, where there is actually an internal state inside of the LLM that we can reuse in between those autoregressive forward passes to effectively skip most of the computation during the decode phase of LLM inference. And so this is a diagram, but on the top, inside of the attention layer, it turns out is the only layer inside of the model that needs to look back at prior tokens. And these K and V state that you can see here, these can effectively be cached. You can reuse them in between each forward pass. And this is a very, very profound change because you shift from having to recompute all of the prompt tokens over and over and over again to basically only having to compute one token during the decode phase and basically reusing that KV cache state. So that equation I have on the left-hand side, it looks small in terms of the terms, but the amount of compute needed in that bottom equation is 1 over the number of tokens in your sequence. And so this is a really, really profound optimization. But the trade-off is that KV caching is a much more complex system. And the reason it is because the KV cache is actually very, very large. So if we think about a model today, like this is, I think, for Llama 2, so this was a case on an A100 40 GB that the KV cache could take up almost half of the memory of the system. A good mental model right now is for a request hitting Llama 370B, is basically every 10,000 tokens is a gigabyte of RAM. And on an H100, B200 server, you're going to have very, very long requests and hundreds of requests active in the server. This can easily add up to gigabytes plus of kind of RAM that needs to be managed. So this KV caching optimization is really important, but creates a really big challenge of, okay, now how can we actually manage this KV cache memory in a fine-grained way? And so VLM's original innovation, if you look at the papers that talk about VLM, was to use a technique that we call page detention. And since there's a lot of folks who maybe understand operating systems inside of this room, the way that we actually manage this KV cache memory is similar to how an operating system manages virtual memory. So basically, every single request has a view of its logical KV cache, where this is an example, Alan Turing is a computer scientist and mathematician. Request A kind of has a view of this logical KV cache, but these actual KV cache blocks can be in random access in the actual physical KV cache table. And the page detention algorithm is basically a fused gather attention operation which uses this mapping from logical to physical blocks to gather the actual KVs that are needed for that individual request in a fused and efficient manner. So this is kind of the original innovation inside of VLM, was to take continuous batching, take KV cache management, and use the ideas from operating system around managing virtual memory with a logical view of every request that allows for really fine-grained management of the KV cache. This was the original innovation that really kicked off the community around VLM, and is the fundamental way that all LLM servers work today. Even systems that aren't based on VLM proprietary systems, they all kind of use this KV caching page detention mechanism at their core. And the reason it's called VLM is the V, it's not an official thing, but the V is like the homage to the virtual memory kind of subsystem. So there's a really great blog that came out last week from someone in the community who really did a really deep dive into the VLM subsystem. But I'll just talk a little bit about how it works today. So we have two parts. One is the kind of metadata management. So on the CPU side of VLM, we have something that we call the KV cache manager. And basically every single block in the KV cache has some metadata associated with it. And all of these blocks start in a free kind of pool. And then on the GPU side, we have the actual physical RAM where we store the KV caches. And that metadata on the scheduler side maps to the actual physical side on the actual GPU. And so when a prompt comes in, effectively what happens is we take the prompts, we tokenize them into their actual indexes that get passed to the model. So if we have hi, my name is, This can be tokens 1, 2, 3, 4, 5. And inside of the LM scheduler, we take blocks from that free block pool and allocate them to individual requests. So for instance, request 1, which has tokens 1, 2, 3, 4, 5, maybe we'll get 2 blocks. The first 4 tokens will get mapped to block 1. The 4th and 5th token will get mapped to block 2. And so on the scheduler side, we take the requests, we allocate blocks, and remove them from the free table, and then we map individual tokens into those blocks. Then during the VLM side, like on the GPU side, during the forward pass, the actual physical RAM will be empty. And during the forward pass, we use the metadata that the scheduler gave us. So the scheduler gave us what's called like a slot mapping, which tells us where every individual token should be inserted into the KV cache. And so during the forward pass of the model, after the Ks and Vs are computed, we inject those during the prefill step, which is the prompt processing, we inject the actual KV values into that kind of persistent KV cache memory using the slot mapping data that the scheduler gave us. And so this is like an example where request 1 got allocated block 1 and block 2, and the tokens get injected into those blocks. Request 2 got blocks 3 and 4, and the tokens got injected into those blocks. And then request 5, or request 3 got block 5. And you can see that we're doing this in a very fine-grained way, where it's not as though every request has a huge static allocation for its maximum possible context. We're doing this in like a greedy way where we're utilizing the actual physical memory in a kind of on-demand basis. And then during the decode step, the same thing happens. We allocate more blocks to the requests. We use that slot mapping data during the forward pass to gather, to do the attention, and then the new tokens get injected. And so on the next step, this request 2 that now has filled up its blocks, it will get a new free block during the forward pass, and so on and so forth. So this is a high-level view. I know this is a little bit of detail, but the overall idea, you can see, kind of during that actual forward pass of the model, how this kind of page detention mechanism works, where the scheduler is kind of managing all of the data, and the GPU, we're utilizing the memory in a very fine-grained way. And then one other advanced kind of piece is, and you might be able to tell this, is since this KV cache memory is static, we can actually share KV caches between requests. So an example kind of interesting feature that builds on top of this subsystem is something called prefix caching. It's very common for requests to kind of share prefixes. You might be familiar with the concept of like a system prompt inside of an LLM request that every single request is reusing in the exact same way. And so in VLM, we can naturally share these requests by injecting another layer of indirection into our block table. And basically every single block that I talked about has a hash value associated with it. So we take the tokens and we create a hash, and that block will be immutable for its life. And effectively, there's actually one additional step in our overall allocation process, which is that if we detect a prefix cache hit where the tokens for an individual request match something in our block table, we can actually just reuse that. And so prefix caching is another really important optimization that kind of leverages our subsystem. I just wanted to mention prefix caching briefly because we'll come back to it in a second. All right, so that's VLM. That's the overall idea. There's lots of other stuff going on in VLM to make the models fast, but if I had to boil the essence of the system down, it's those two things. It's continuous batching and it's KV cache management. Those are the fundamental problems that an LLM inference server is solving, and we have an elegant solution to this inspired by virtual memory, and that subsystem sits at the core. So what is llm-d then? Well, it turns out that just like how in the individual inference server, we can take advantage of cluster level, just like inside of the inference server, we can take advantage of the architecture of the transformer to make things more efficient. We can apply this to a cluster scale as well. So llm-d takes the idea of saying, okay, inside of VLM, we're able to exploit the properties of KV cache and auto-arrested inference to make a more efficient thing than if we had something naive. llm-d says, okay, what if we looked at that at a cluster level and implemented optimizations inside of Kubernetes that allows us to exploit this kind of fundamental KV caching subsystem to get performance advantages. And so why is there an opportunity to do this? I think it's fundamentally that LLM requests are different from standard HTTP requests. Standard HTTP requests, have the following properties. They're fast, they're uniform, they're cheap. So very standard practices on top of Kubernetes is to have a deployment, scale out the number of replicas, put a service in front of that, do a random load balancing between the different pods, and everyone's happy, it's easy, and you have a nice scale-out system. It turns out for LLMs, you can do a lot better than that, and the reason is that that's actually not how LLM requests typically look. For instance, we have certain requests that are really, really small with really, really long generation phases. We often have repeated patterns where users will send the same prompt with extensions on it back to the model server over and over and over again in an agentic pattern where maybe they're calling a tool and then sending the request back, or it's a multi-turn chat kind of conversation. So there's opportunities to leverage that KV cache. I'll give you a look ahead. And also, as I mentioned, there's a prefill and decode phase. And so there's an ability to kind of specialize the servers for each one of those phases. So in general, the overall idea with LLMD is these two things. It's modern HTTP requests work really well for round-robin kind of scale-out load balancing. LLM requests don't look anything like that. They have really, really, really long examples. They take multiple seconds. We have this kind of repeated pattern, so opportunities to exploit the cache, and there's opportunities to actually coordinate replicas together to get a better kind of performance outcome. And so that's the overall idea with LLMD, is to bring these two things together inside of the Kubernetes operational model. And so this is a high-level diagram, but the overall way that LLMD works is we build on top of Gateway API, which is a kind of core Kubernetes upstream project that's effectively the replacement for Ingress. And we hook in LLM-specific scheduling logic into Gateway. So for instance, if a request comes into the system, Gateway will use what's called an XProc, send the request out to an endpoint picker, which we call the inference scheduler. The inference scheduler can execute arbitrary logic for scheduling things onto the cluster. It should have a view of the load, the current KV cache state inside of each of the replica, and the inference scheduler makes the decision about where the request should go. And then inside of the inference pool, we can do arbitrary configurations. We can do a prefill decode disaggregation setup. We can offload to other KV caches. So I'll just talk through a couple examples, but this is the overall architecture of LLMD, where we have a gateway, which is taking requests in. We have an inference scheduler, which is in charge of making the decision for how the request should be processed. And then we have the inference pool, which is responsible for actually executing the request. So the first example that I think I'll talk about is how we can use LLMD to exploit that prefix caching feature that I talked about in VLLM before. So the first thing to kind of understand is it's very, 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 very common for LLM requests to have repeated prompts. Think about the way that you might interact with the chatbot. Very often, you're going to have a multi-turn conversation where each prompt that you're actually sending to the model is all of the chat conversation history plus a little bit more. You can think about an agentic tool calling loop where the model is generating some reasoning tokens. It says, okay, I need to call this tool. It calls the tool. The result of the tool comes back into the model, and you keep generating from there, right? And so it's very, very, very common to have repeated prompts coming back to the VLLM server. So a big problem is if you're just deploying a Kubernetes service in a deployment, if you have 4 replicas of VLLM, if a request in that repeated pattern gets randomly assigned to a VLLM pod, you're going to have cache misses that you otherwise could have used. And so what LLMD, one of the core features of LLMD is what we call prefix cache aware routing, where EPP has some notion for each of the VLLM pods of the current view of the KV cache state. We actually have two versions of this. One is inside of EPP, we maintain an approximate prefix cache tree where the EPP, the inference scheduler, effectively will approximate the current state of the KV cache for each pod. And then we have a precise version of this where VLM will actually publish events, and the inference scheduler will subscribe to those events, which has actually a globally consistent view of the current state of VLM's KV cache. And so EPP can then make a decision, for an individual request. Oh, I know that the KVs for this request are available in pod A. Let's send that request to pod A. So you can see how LLMD, with this prefix cache-aware routing feature, is able to actually exploit the properties of VLM subsystems to get a very, very significant performance win. And something like prefix cache-aware routing is absolutely critical for modern deployments of LLMs, where these sticky sessions will have dramatic impacts on the P90 latency that users will face. So I had a little bit of a demo of this, but I'm taking a little bit too much time, so I'll skip it. But another example of how we can leverage the KV cache subsystem is a feature that we call PD disaggregation. So I talked a little bit before about the prefill and decode phases of LLM inference, where inside of the server we have the prefill phase, which is processing the prompt, and then we have the autoregressive decode phase, which is generating the tokens. And so one overall idea is these are actually quite different computational problems. And so an idea is, what if we specialize VLM servers such that some of them are specialized for prefill, some of them are specialized for decode? So if you've been following, one of the key things that would be needed for this is what's called a KV cache transfer, where after processing the prefill, if we can send the KV cache from the prefill instance to the decode instance would never have to process the prompt. So again, we can exploit the properties of the KV cache to build a distributed system that allows us to specialize for specific components of the VLM process. So for example, in a PD disaggregation deployment inside of LLMD, a request comes into the gateway sends it out to the inference scheduler. The inference scheduler will make a decision to say, okay, should this request be processed as PD disag or as a regular request? It will also schedule to the prefill and decode instances that have a KV cache hit or have no low load. And then, okay, if it decides that the PD disag, we'll send it to the decode pod first. The decode pod has a sidecar, which effectively coordinates the transaction, forwards the request to the prefill instance. The prefill instance processes the request and basically appends some metadata, which tells where the KV blocks are in its memory. It's using actually the same block IDs that I talked about in the previous VLM system, sends that back to sidecar. Then the decode instance uses that KV transfer metadata to pull the KV caches from the prefill instance into the decode instance. This has to happen very efficiently. I already talked before about how the KV cache can be a gigabyte per every 10,000 tokens. And so we leverage some high performance libraries called Nixel, which is NVIDIA Inference Transfer Library, which basically does an RDMA transaction to pull the KV blocks GPU direct to GPU direct. And PD disaggregation is a really significant performance optimization. This was an example running GPT OSS with 4,000 input tokens, 4,000 output tokens. This is what's called a Pareto chart. So the x-axis shows the tokens per second per user, the y-axis shows the tokens per second per GPU, and each dot is a concurrency in the system. So basically, this is running with 8 GPUs. These dots in the center here show the results at 100 concurrent users. And what we can see is that the PD disaggregation improves the latency, the number of tokens per second per user by about 25%, in comparison to the aggregated setup. And so you can see that using these techniques where we exploit the property of the KV cache allows us to improve the overall performance of the system. And the last thing I'll just mention is I obviously have been talking a lot so far about the KV cache subsystem inside of the VLM. So far, this has all been resident in GPU memory. there also are basically heavily underutilized other resources inside of these massive GPU servers. So an example is CPU RAM. So a very obvious optimization is let's not evict requests when we run out of GPU memory. Let's offload those to CPU RAM. And this allows us to expand the size of the KV cache and to allow us to hold more requests resident in memory without having to recompute in so many cases. And then there's a large series of vendors which have been working on basically GPU direct storage. So examples are vendors like Weka or Vast, which do GPU direct storage to the NVMe drives. And so a lot of these folks have been working on some new features to not only offload to the local resources inside of the LLM pods, but also to remote KV cache indexes, which allows us to expand the size of the KV cache. So this is another example of a feature where we can, at the cluster level, exploit the properties of the LLM subsystem to get a globally better system. So there's other features inside of LLMD, but I think you kind of get the point. The overall idea is let's exploit the properties of the LLM server to get a globally better cluster optimization. And hopefully this was interesting. I know this is a pretty technical talk, but I think the overall summary is VLLM and LLMD are fundamentally systems projects that are exploiting the properties of the transformer to get the best possible performance. So if you're interested at all in how LLMs work, if you're interested at all in systems programming, trying to squeeze high performance, this is a really great kind of project and ecosystem to be working in, since I find it very interesting, and also there's lots of innovation going on. So, I've abstracted away the kind of overall concept of a KV cache, but the model vendors are continuously pushing on, implementing and improving the way that KV caches work. So, DeepSeek with their MLA, GPT OSS leverages something called interleaved sliding window attention, where there's certain layers that only attend to, a smaller number of tokens. There's lots of innovation happening in the kind of model vendor space, and it's our job across this whole stack to take in those new optimizations and make all of these kind of concepts work. So please get involved if you're interested in any of these techniques, and happy to take some questions now. Thanks.